Sir, I'm back.
So, am I audible? Are you getting my voice? Hello.
Yes, sir, you're
Okay. So in the last class, we discussed the mass defect and binding energy. We have discussed the mass defect and binding energy. So what is mass defect? During the formation of nucleus, some mass is disappeared. That is known as the mass defect. And energy corresponding to that mass defect is the binding energy. After that, we discussed the nuclear stability. We have seen the graph between the binding energy per nucleon versus the mass number. Okay, we have seen this kind of graph. Okay, for lighter nuclei, the binding energy per nucleon is less. For example, take hydrogen, this hydrogen, okay, of mass number 2. So binding energy is least, and maximum binding energy is seen in iron. Binding energy per nucleon is for iron nucleus. Okay, and after iron, the binding energy per nucleon again decreases, and least binding energy per nucleon is of uranium-238. So we have seen these things in the last classes. Today we will discuss one more thing. I told you in the last class, this uranium-238 nucleus is unstable because of less binding energy. Approximately this is having 7 mega electron volt of binding energy per nucleon. So due to the less binding energy per nucleon, this uranium-238 or this uranium is unstable. So to get the stability, this nucleus will split into smaller nuclei to get the stability. Obviously, the smaller nuclei will have more binding energy per nucleon as compared to uranium-235, that is splitting. So today we will discuss the nuclear fission and nuclear fusion. So first we will discuss nuclear fission. So what is nuclear fission? So nuclear fission is a process in which the heavy nuclei split into 2 or more larger nuclei along with the release of energy. And why the energy release? Due to the mass defect. So nuclear fission. So what is nuclear fission? First point, nuclear fission is a nuclear reaction in which a heavy nucleus, for example, the nucleus of uranium-235 you can take, splits into 2 or more lighter nuclei. So for example, suppose you have this nucleus. Suppose you have this nucleus, and this nucleus is splitted splitting into smaller nuclei. These are smaller nuclei. So this is the parent nucleus, and these are the daughter nuclei. Parent nucleus, daughter nuclei. So this nucleus here can break into 3 daughter nuclei also. Okay, but mostly it will break into 2 daughter nuclei, mostly. So second point, most of the fissions are binary, means the parent nucleus will split into two daughter nuclei. Binary means two daughter nuclei we will get. Okay. 4 out of 1000 are ternary. 4 out of 1000 are ternary means if 1000 fissions are taking place, 1000 fissions are taking place. So in those 1000 fissions, only in 4 fissions there will be splitting of nucleus into 3 daughter nuclei. Ternary means 3, binary means 2. Okay, third point, the daughter nuclei are of comparable size. So here we are getting the daughter nuclei. So these daughter nuclei are of almost same size. Okay, size of this nucleus and size of this nucleus will be almost same. Now there are two types of fission, you can say spontaneous fission and induced fission. Spontaneous fission example is radioactivity. And induced fission is the fission which is started by some element like proton, like neutron, like alpha particle, and after that, that fission will continue by itself. Initially, the fission is started by some particle like proton, neutron, alpha particle, and after that, it will be self-propagated. So this is induced by proton, you can say, or it is induced by the, you can say, alpha particle, or it is induced by neutron. So the fission induced by neutron we will study. Okay, this is in our syllabus, so we will study this. Okay, the fission which is induced by the neutron. Fission which is induced by the neutron. So now see this diagram. In this diagram, here I have taken a uranium-235 heavy nucleus because it is having a mass of 235 AMU. So this is a heavy nucleus. So uranium-235 will show the nuclear fission. Okay, and this nuclear fission will be induced nuclear fission. Basically, there will be a use of a slow neutron to start the nuclear fission. So this is the uranium-235, and inside this is the nucleus of uranium-235. So inside the nucleus, these are the nucleons, means protons plus neutrons. These are protons plus neutrons. So this is a neutron. Okay, this is a neutron. And this is a thermal neutron. The thermal neutron means the energy of this neutron, the energy of neutron is due to the, you can say, due to the room temperature. Due to the room temperature, the energy possessed by the neutron is thermal neutron, and it has energy of 0.025 electron volt of energy this have. So what will happen? This neutron, this thermal neutron will enter into this nucleus. So inside this nucleus, one nucleon will increase. Okay, now it becomes uranium-236 because one neutron increased, so it will become uranium-236, and this uranium-236 is unstable. Uranium-236 is unstable. So if this uranium-236 is unstable, so this will further split into daughter nuclei. Okay, this is uranium-236, and after that it will become like this, and after that it will be splitted. And during this process, sometimes 3, sometimes 4 neutron will release. So here 3 neutrons are releasing. So these are daughter nuclei. These are daughter nuclei. So we can write this process in the form of the equation. So initially we have uranium-235 and we have given 1 neutron to it. Okay. And what we get? Uranium-236. What we get? Uranium-236 and it is 92. The atomic number of uranium is 92. So this we will get. And now this is unstable. So if this is unstable, so this will break into daughter nuclei. It is 92 and this is 236. So this nucleus of uranium-236 will split into smaller nuclei of barium plus krypton. Okay, so barium having atomic number 56, mass number 144, krypton having atomic number 36 and mass number 89. Okay, so this uranium-36 will break or split into barium and krypton. These are lighter nuclei and this is heavy nuclei. And along with barium and krypton, 3 neutron will release. 3 neutron will release and plus energy will release. Energy will release. So now you can balance the mass here also. It is 236. It is 236. Now add this 144 and 89 and 1. 89 and 1, 90. Okay. And 90 and 144. Sorry, it is 144 and 89. And this is 3. Okay. Because you will because here are 3 neutrons. So you will add 1 plus 1 plus 1. So mass will become 3. 3 plus 89. 92 and 92 and 144. 92 and 144 is 236. So this mass is balanced here. Okay. Understanding, Hamza, what is nuclear fission? Then we will move to the next topic, energy in nuclear fission. Energy in nuclear fission. Okay. Now energy in fission. So this is this curve we earlier also we studied this curve, binding energy per nucleon versus mass number. So this is the type of curve we have approximately, and iron has the maximum binding energy per nucleon, and here somewhere will be uranium-236. So this uranium-236 will have approximately 7.6 mega electron volt of energy. Okay, mega electron volt of energy. So basically this binding energy per nucleon is in mega electron volt. So this is having the less binding energy per nucleon. So this uranium, this is uranium-236. So this uranium-236 will break into barium and krypton. And barium, these are barium and krypton. You can consider these having the more binding energy per nucleon as compared to this uranium nucleus. Okay, so you can say this uranium-236 is less stable. And these two daughter nuclei are more stable. So from the curve also you can understand why the fission is taking place, because this is unstable. This uranium-236 is having less binding energy per nucleon. Barium and krypton is having more binding energy per nucleon. So this is getting stability by splitting into barium and krypton. Okay. So now here if we are taking one uranium-235 nucleus, one nucleus of uranium-235, on fission of one nucleus of uranium-235, 216 mega electron volt of energy is released. One nucleus of uranium-235 on fission releases 216 mega electron volt of energy. So in the fission reaction, earlier also I told you, energy is releasing. Energy is releasing. If energy is releasing means some mass will disappear. Some mass will disappear. So we will now calculate how much mass of uranium will disappear. How much mass of uranium will disappear. So we know that if the energy of 931.5 mega electron volt is releasing, then 1 AMU mass will disappear. Now here, how much means how much amount of energy is releasing? 216 mega electron volt of energy is releasing. So 216 mega electron volt of energy releasing, and we want to find what is the mass disappeared corresponding to this energy. Very easy. From this equation, okay, from this equation you can find, okay, take this equation here. So from this equation, okay, from this equation, if 931.5 mega electron volt energy is releasing, then 1 AMU mass will disappear. If 1 mega electron volt energy is releasing, then how much mass will disappear? 1 divided by 931.5 AMU. If 216 mega electron volt of energy will release, then how much mass will disappear? It will be 1 divided by 931.5 multiplied by 216 AMU. This much mass will release. So this is approximately equal to 0.23 AMU. This is approximately equal to 0.236 AMU. Means this much energy we are getting from this much mass disappearance. Okay. So basically you can say mass disappear during fission of uranium-235 is equal to 0.23 AMU. 0.23 AMU. Okay. Fission of one nucleus, you can say one nucleus of fission of one nucleus of. So what is the mass of one nucleus of uranium-235? 235 AMU will be the mass. Okay, 235 AMU will be the mass. So you can say out of 235 AMU, 0.23 AMU mass will disappear. So now you can calculate the percentage mass that is disappearing during the fission of one nucleus of uranium-235. So percentage mass that is disappeared that is equal to the mass disappeared divided by the total mass, means 0.23 divided by 235 and multiplied by 100. So this will be approximately equal to 0.1%. So you can say only 0.1% mass of uranium-235 is used in the nuclear fission reaction. Or you can say only 0.1% mass of uranium will disappear during fission reaction. Okay, Hamza? Understanding? Hamza, hello? Beta, are you getting or not? Hello, Hamza? Hamza, hello? Hamza, hello? Hamza, are you there?
Yes, sir.
Okay. So are you getting it? Am I audible or not? Okay.
Sir, your voice is
Okay. Now it's okay?
sir, it's breaking. It's becoming low at the end.
Okay, okay. Hello? Now it's fine? Just a minute.
Still the same. Thing
Just a minute.
it's breaking a little bit. Starting, it's fine. Then at the end, it will.
Yeah. I can understand now. I think now it will be okay. Is it fine or same? Now it's fine, Hamza? Hello?
Yes, yes,
Now
sir.
it's now it's fine now?
Sir, it's still the same, sir. So I think you should remove headphones and join the headphones again.
Hello? Now it's fine?
Yes.
Hello?
Now it's loud.
It's lagging. Now also it is lagging.
Sir, it's fine now.
It's fine now? Okay. Just give me one answer if I am saying that 10% of 25. What will be the answer? 10% of 25. What is 10% of 25? Hello, Hamza. I think now my voice is also fine. Hello? %10 of 25 means 10 by 100 multiplied by 25.
Yes.
So it will become 2.5. Okay. So now we will discuss the chain nuclear reaction. So what is chain nuclear reaction? Here is a thermal neutron. This thermal neutron is entering into the uranium-235, and fission of this uranium-235 will take place, and 3 neutron will release. It will release 3 neutrons. Okay. So now see this neutron. This neutron will again collide with uranium. This neutron will again enter into the uranium, and again the fission of this uranium will take place. Again 3 neutron will release. Okay. Here also fission will take place of this uranium due to this neutron, and 3 neutrons again will release. Here also 3 neutrons will release, and this process will continue. Here how many fissions are taking place? Only one fission of uranium. Here is a fission of uranium-235, one uranium-235, and here fission of 3 uraniums, and here the fissions of 9 uranium will take place. So basically this will become a chain reaction. This will become a chain reaction. Here 1 fission, 3 fission, 9 fission, 27 fission, 81 fission, and so on. Now this chain reaction, if this nuclear reaction is like this, so it will become uncontrolled. And if it will become uncontrolled means what I want to say is the energy release rate will increase tremendously. Okay, the energy release rate will increase so much. Okay, and difficult to control. So uncontrolled chain reaction, when one fission causes more than one fission. So here due to this fission there are 3 fissions are taking place, and due to this 3 fissions 9 fissions are taking place. So due to one fission more than one fissions are taking place. So basically this is a case of uncontrolled chain reaction. So in uncontrolled chain reaction, energy release will multiply, means tremendous amount of energy will release in millisecond. And basically this uncontrolled chain reaction is used in atom bomb. Okay, is used in atom bomb. For example, if you are taking 5 kg of uranium, 50 kg of uranium, you can get 10 to the power 15 joules of energy. So basically in the previous years, in 90s, so there was a incident in Hiroshima, that is in Japan. So USA
Yes, sir, I know.
What are you saying? Do you know about this Hiroshima blast?
What?
Yes, sir. Hiroshima, Nagasaki.
Hiroshima and Nagasaki. So what they did? They dropped one atom bomb. And what is happening in atom bomb? Chain reaction, uncontrolled chain reaction. And uncontrolled chain reaction means just now we calculated the energy in the fission. So what we are getting for one nuclei from the fission of one nuclei of uranium-235, we are getting this much of energy. So if 50 kg if you will use, it will destroy the whole city. Due to large amount of energy will release. But it is in case of when uncontrolled chain reaction will takes place. Uncontrolled chain reaction means due to one fission more than one fission will take place, as in this case. Here is one fission. Here is, due to this fission, 3 fissions are taking place. Due to these 3 fissions, 9 fissions are taking place. And due to these 9 fissions 27 fissions will take place. So basically, this is a geometric progression: 1, 3, 9, 27, 81. After that, so basically they dropped a atom bomb, and there is a blast of atom bomb. Basically, in atom bomb, there is a fission reactions are taking place, uncontrolled fission reaction, and due to that, a large amount of energy released, and due to that, there is a large amount of destruction also. Now, controlled chain reaction. Controlled chain reaction means one fission causes one fission. One fission causes one fission means this is a thermal neutron. This thermal neutron will enter into the uranium-235. So fission of uranium-235 will take place, and 3 neutron will release. So out of 3 neutron, you have stopped 2 neutrons somehow. Only 1 neutron now will do the fission of further uranium. So now from one fission, here only one fission is taking place. Now from here, this fission will take place, fission of this uranium will take place from this neutron, and again after fission of this uranium, 3 neutron will release, and again you have stopped 2 neutrons for further fission. So there will be only one fission now. So like this, due to one fission, when there will be only one fission. Due to one fission, when there will be only one fission. That is the case of the control chain reaction. So in control chain reaction, one fission causes one fission. And if one fission causes one fission, means energy will release in a controlled manner, or rate of energy release or rate of energy liberated will remain constant. And that is used in the nuclear reactor. That is used in the nuclear reactor. And why? What is the use of the nuclear reactor? There are many uses, but one of the use of the nuclear reactor is to produce the electricity. Is to produce the electricity. Okay, Hamza, understanding? Hamza, hello. Now my voice is fine now. Should I move now to the next topic? Hello. Should I move now to the next topic? Hello, Hamza.
Yes, sir.
Are you getting or not?
Sir, again,
Hmm?
it's stopping.
Should I explain again?
No, sir, that part, now your voice is lagging again.
Oh, my voice is lagging again.
Yes,
Just
sir.
give me 1 minute. Don't know why today my voice is lagging. Hamza, please check your internet. Hello? Hamza, my internet is okay. Please check your internet. Maybe your downloading speed is slow. Hello, Hamza. Hello.
Okay.
I'm saying, please check your down speed of internet.
I- I'll check. Should I rejoin?
Hmm? Hello, Fawaz. Hello, Fawaz.
Hello, yes, sir.
How are you?
I am fine.
My voice is okay?
Yeah, yes, perfect. अभी तक स्टार्ट नहीं हुई थी क्लास.
Actually, I have started, but Hamza is getting some problem, so that is
Oh,
why he is joining again.
oh, okay.
We have started, so we can revise till then
Okay, sir.
what we have done. So I have started from nuclear fission. So basically, nuclear fission is the splitting of heavy nuclei into smaller and lighter nuclei. Okay, and spontaneous fission is radioactivity, and induced fission is like this. Okay, you have to do some extra effort initially, but after that the fission is self propagated. Hmm? After that the fission is self propagated. uh, this is uranium 235, and these are the nucleons, uranium 235 nucleus, and these are the neutrons, and these are the protons and neutrons of this uranium 235. And we are using a thermal neutron. Thermal neutron means the neutron having the energy corresponding to the room temperature. That is known as the thermal neutron. Basically, thermal neutron have the less energy. So due to this, the fission is taking place. This neutron is entering into this nucleus uranium 235, and it is getting uranium 236. And uranium 236 having less binding energy per nucleon as compared to uranium 235. So this is unstable, and if this is unstable, so it will break into the smaller nuclei. And I have written here equation. Okay. So you can take the screenshot of this. Energy in fission, I have discussed. In fission of one nucleus of uranium-235, you will get 216 mega electron volt of energy. Mega electron volt of energy. If I told you that if energy will liberate, then there will be the mass disappear. So we can calculate the amount of mass that has been disappeared during the fission of uranium-235. So basically, when you will calculate, you will get approximately 0.1% of the mass will be disappeared during the fission of uranium. After that, we have discussed the chain reaction. So chain reaction is this. Hamza, now it's okay. Now it's fine now. Fawaz, now it's
Yes,
fine.
sir.
Okay.
Yes.
Okay. Now see. Again, I am telling. This is uranium-235, nucleus of uranium-235. This is a thermal neutron. Thermal neutron is entering into the uranium-235. So due to this neutron, thermal neutron, the fission is induced and fission of uranium-235 will takes place. And fission will takes place. And what I told you during this fission, during the fission of uranium-235. So how the fission of uranium-235 takes place? So this is neutron. Okay, you can see here is neutron, and this neutron is entering into uranium-235. So neutron, uranium-235, after combining, it will become uranium-236. So this uranium-236 will split now into barium and krypton, and 3 neutron will release along with energy. So in chain reaction, you can see fission of this uranium-235 will take place and 3 neutrons will release. And now further fission of uranium will take place by these neutrons. Now suppose here is another uranium nucleus, and this neutron will enter into this, and fission of this uranium will take place. Same here, the fission of this nucleus will take place. Same here, the fission of this uranium nucleus will take place. On one fission, 3 neutrons will release. Okay, 3 neutrons will release, and this process will continue. This process will continue. Means here will be another nucleus, and from that nucleus again 3 neutron will release. Here will be another nucleus, from that nucleus 3 neutron will release. Okay, here will be another nucleus, from that nucleus 3 neutrons will release, and this process will continue. So basically this is a chain reaction. So from one fission, 3 fissions are taking place. From these 3 fissions, 9 fissions are taking place. From these 9 fissions, 27 fissions will take place. From 27 fission, 81 fissions will take place. It will be a geometric progression. 1, 9, 27, 81. After this, I told you what is uncontrolled chain reaction. So basically, this is an uncontrolled chain reaction. From one fission, if there are more than one fissions are taking place, then it will be an uncontrolled chain reaction. So you can see here is only one fission taking place. Now from this one fission, 3 neutrons we are getting 3 neutrons, and from with the help of these 3 neutrons, 3 fissions of uranium taking place. So from one fission, 3 fissions are taking place, and from these 3 fissions, 9 fissions will take place. So basically we can say this is the uncontrolled chain reaction. Why? Because from one fission, more than one fissions are taking place. And what will happen in this case? We know that during the fission of uranium-235, one nucleus of uranium-235, 216 mega electron volt energy is releasing. So means you can say energy is large amount of energy will release during the fission of uranium. So in case of the uncontrolled chain reaction, the energy liberated rate will be very large. Okay, energy liberated rate will be very large. So uncontrolled chain reaction, when one fission causes more than one fission, energy release will multiply in milliseconds. Okay, and basically this uncontrolled chain reaction is used in the atom bomb. For the 50 kg of uranium, you can get this much of energy, and I told you about this also. Controlled chain reaction, one fission causes one fission, means here one fission is taking place, 3 neutron will release. Somehow you have stopped 2 neutron for the further fission. Now only one fission will take place here. Now from this fission, 3 neutrons again liberated or released. Somehow again you have stopped 2 neutron for the further fission. So here only one fission will take place. Now from one fission, only one fission taking place. From one fission, only one fission is taking place. So basically, this is a control chain reaction. In control chain reaction, from one fission, there is only one fission taking place. One fission causes one fission. In this case, less number of fissions are taking place, so energy liberated rate will be constant. Okay, and control chain reaction, controlled nuclear reaction is used in the nuclear reactor, and nuclear reactor is used to produce the electricity. Understanding, Fawaz and Hamza?
Yes, sir. Yes, sir.
Okay. Now there are some difficulties in the process of chain reaction. Number one, poor concentration of uranium 235. Poor concentration of uranium 235. So in nature, uranium is founded in two forms: uranium 238 and uranium 235. So basically, this uranium 238 is 99.3% in nature, and this is 0.7%. For example, if you have 1000 kg of, if you have in 1000 kg natural uranium, seven kg of uranium 235 you will get, and 993 kg of uranium 238 you will get. Now we have this in large amount and this in very small amount. So what will happen when we will do the fission of uranium 238? So now you can see here, uranium 238 is non-fissile. Uranium 238 is non-fissile. So what is the meaning of non-fissile? Non-fissionable by thermal neutrons. Thermal neutrons. So the fission of uranium 238 cannot be achieved by the thermal neutron. Thermal neutron means neutrons having less energy. So uranium 238 can only be fissioned with high energy neutrons. So high energy neutrons of energy 1 mega electron volt or more. Suppose you have somehow given energy of 1 mega electron volt to the neutron. Now fission of uranium 238 is taking place. On fission, 3 neutrons will release, but these neutrons will have the low energy due to the inelastic scattering. So inelastic scattering is like inelastic collision. So in elastic collision, you know that energy is lost. So basically, these neutrons will lost energy. So these neutrons will have less energy. So these neutrons do not have 1 mega electron volt energy due to inelastic scattering, and hence they cannot sustain chain reaction. After that, instead these slow neutrons are absorbed by uranium 238 and beta decay occurs. So these neutrons will be absorbed by the further uranium-238 and beta decay will occur instead of nuclear reaction. The fuel uranium-235 is now we will see how the fission of uranium-235 will takes place. The fuel uranium-235 is fissionable only by slow neutron. I told you that the fission of uranium-235 will take place by the thermal neutron or slow neutron. Slow neutrons having energy of 1 electron volt or thermal neutron having energy of 0.025 electron volt. Okay, so this is thermal neutron of 0.025 electron volt energy. This is entering into uranium-235. So fission of uranium-235 will take place, 3 neutrons will release, but these neutrons will be of high energy. But for the fission of uranium-235, there is a requirement of low energy neutron. But here, what is happening? For the fission of uranium-238, there is a requirement of high energy neutron. But what we are getting after fission? Low energy neutron. Here, there is a requirement of low energy neutron for the fission of uranium-235. And what we are getting? High energy neutron. So each of these neutrons means these neutrons have 2 mega electron volt energy. So we have to slow down these neutrons to low energy so that they can cause further fission. Another problem is the problem of the critical mass. So what is the critical mass? First understand what is critical mass. So critical mass depends upon the geometry of the fuel and the speed of the neutron. Even slow neutrons move at 8 times the speed of sound. Slow neutrons also moves very fast. If the layer of the fuel is thin, the neutrons may pass through it without causing fission. Suppose this is the uranium. If the layer of the uranium is thin, suppose neutron is having high energy or high speed, high kinetic energy. So due to the high kinetic energy, the uranium will pass through this uranium. So if the neutron will pass through this nucleus, no fission will take place. So there is a minimum mass or there is a limiting mass. For that the fission is sustainable. That mass of the fuel uranium-235 is known as the critical mass. So you can see here there must be a limiting mass of the fuel which can sustain chain reaction. That limiting mass is called critical mass. So critical mass is basically depending upon the size of the nucleus and depending upon the speed of the neutron. More will be the speed of the neutron, more thickness it can penetrate. More thickness of the fuel it can penetrate. Fuel means uranium-235 we are talking about. Hamza and Fawaz, both of you, please now take these screenshots.
Yes, sir. Done.
Okay. Okay, take.
Yes, sir. Done, sir.
Done. Hamza, you also please take the screenshot.
Done, sir.
Okay, take this screenshot.
Done, sir.
Okay, take this.
Done, sir.
Okay, take this.
Yes, done, sir.
Okay. Okay, take this.
Done, sir.
Okay, good.
Done, sir.
Take this screenshot.
Done, sir.
Okay.
Done, sir. Done, sir. Done. Done, sir.
Okay.
Yes, sir. Done.
Okay.
Done.
Okay. So I have not explained this. Now I will explain this. Okay. Screenshots you already taken. So controlling rate of fission. Controlling rate of fission uh, is this K. K is the rate of fission. So what is the rate of fission? Number of fission in present generation divided by number of fission in previous generation. So this we can explain with the help of this diagram. Suppose right now we are here. Right now we are here. This is the present number of fission in the present generation. 3. And this is these are the fission in the present generation, and these are the fission in the previous generation. Suppose if we are here, if this reaction is here, okay, remove this. If this reaction is here, suppose at this point of time, then this will be considered as present generation. So present generation means how many fissions are taking place here? 9. And in previous generation, 3 fissions are taking place. So this is the value of K. If K is equal to 1, means number of fission in present generation will equal to the number of fission in previous generation. Case of the controlled chain reaction. Okay. One fission causes one fission. Controlled chain reaction. Controlled chain reaction. If there will be a controlled chain reaction, rate of energy is constant. If K is greater than 1, means uncontrolled chain reaction. By one fission, there will be more than one fission. So one fission causes more than one fission. Uncontrolled chain reaction, and we know that large amount of energy will be released in less time. So rate of energy liberated increases. Okay, increases. K is less than 1. K is less than 1 means earlier there are 3 fissions taking place. After that, 1 fission is taking place. So basically energy liberation will decrease or number of fission will decrease. After that, we will discuss the nuclear reactor and nuclear.
Can you explain again that K is equal to 1 means what?
K is equal to 1 means, okay. K is equal to 1 means you have to understand this. You have to understand this before that. This is the present generation. Suppose here you have given a thermal neutron to uranium-235 and fission of uranium-235 takes place and 3 neutrons are released. Now, okay. Now these three neutrons each doing one fission. Okay. So due to this neutron, the fission of this uranium will take place. Due to this neutron, the fission of this uranium will take place. Due to this neutron, the fission of this uranium will take place. How many fissions are taking place? This is the present generation. This is the present generation. Present generation means right now the reaction is here. The nuclear reaction is at this condition. So how many fissions will take place from here? 3?
3, yes sir.
3. No. And previous generation is previous to this. How many fissions are there? 1.
1.
So the value of K will become 3 divided by 1. Means K becomes 3. So in this way you will calculate K. So now understanding what is K?
Okay, then K is equal to 1 means
K is equal to 1 means K is equal to 1 means suppose somehow you have stopped these fissions. Somehow you have stopped these fissions. Now these 2 neutrons are not doing fission. So how many fissions are in present generation now? 1.
1.
In previous generation, how many fissions are there? 1. So what is the value of the K? Number of fission in present generation, that is 1. Number of fission in the previous generation, that is equal to 1. 1 by 1 is 1. That is K is equal to 1. Understanding?
Yeah, yes sir.
After that, this is the nuclear reactor, and this you have to complete by yourself with the help of NCERT. With the help of NCERT or some reference book, you can complete this by yourself. This is your homework. Okay, Fawaz?
Okay.
So now we will discuss nuclear fusion, last topic. Nuclear fusion. In nuclear fusion, basically what happens in nuclear fusion? In nuclear fusion, 2 lighter nuclei will combine to form heavier nucleus. So nuclear fusion. Nuclear fusion is a process in which two or more lighter nuclei combine to form heavy nucleus. Fawaz and Hamza, just give me 1 minute. Okay.
Okay.
So in nuclear fusion, these two lighter nuclei are combining to form a heavy nucleus. This is heavy nucleus as compared to this, and these two lighter nuclei are combining to form a heavy nucleus. Along with this, a positron is released and one antineutrino is released, and the energy of 0.42 mega electron volt will release. Fusion means combining by melting, okay, blending by melting, you can say. Okay, now I will explain you how fusion reaction takes place. How fusion reaction takes place. Suppose you have taken these two lighter nuclei, 1H1, 1H1. You have taken these two lighter nuclei. So this is the nucleus of this, and this is the nucleus of this, and we know that nucleus have the positive charge. So both these when you will try to combine both these nucleus of this and this, they will repel each other, because positive charge will repel each other due to the electrostatic force. So electrostatic force will act in this direction, in the opposite direction. Both will repel like this. So now what you want? You want to combine these two nucleus, but they are repelling. To combine, you have to do some extra work. Means you have to give some extra energy to the nuclei, and the extra energy that you will give to these nuclei will be given in the form of the kinetic energy. You can see here, if we take any two nuclei, okay, take this nucleus and this nucleus. If we take any two nuclei, they will repel each other. Nuclei with smallest positive charge. So basically, we have taken two nuclei with smallest positive charge. So I have told you why they are repelling. We have to bring one nucleus from infinity. So what you should do now? Bring this nucleus closer to this nucleus. Okay, we have to bring one nucleus from infinity far off distance. Why we are saying far off distance? Because the size of the nucleus is very small. For these nuclei, you can say 10 centimeter is also a infinite distance. We have to bring one nucleus from infinity far off distance to a very small distance. Okay, r tending to 0, very close, very close, by doing an external work on bringing them close enough. So when, after doing the work, when these nuclei will become very closer, after that these nuclei will become very closer, nuclear force start acting, and nuclear force is attractive force. Nuclear force will begin to act. Nuclear force is attractive force, and this is a short range force. Means nuclear force act between two nuclei which are very small distance. And this nuclear force which will act when two nuclei are very close to each other, this nuclear force will be stronger than this electrostatic force. Now, due to the nuclear force, both these nuclei will combine and fusion reaction will takes place. So I told you we will give the kinetic energy to the nuclei so that nuclei can come closer. So we give the kinetic energy to the nuclei, and how we can give the kinetic energy to the gas molecule? This hydrogen is a gas, na? So you will give kinetic energy in the form of the heat. You will give the heat, and the molecules will vibrate. Basically, you are giving the vibrational kinetic energy. Molecules will vibrate and move and here and there. So we give kinetic energy to nuclei. We heat the nuclei to supply it with an energy of 400 kilo electron volt. Basically, we will give energy of 400 kilo electron volt to one of the nuclei. Okay, so this much of kinetic energy we are giving in the form of heat. Now, corresponding to this kinetic energy, what temperature to what temperature we have to heat the hydrogen nuclei, that we can calculate with this kinetic energy of a gas molecule is half into K into T. From kinetic theory of gases, kinetic energy is equal to half into K into T, and K is known as the Boltzmann constant and T is the temperature in Kelvin. So kinetic energy, you are giving 400 electron volt. So you will put here 400, you will put the value of Boltzmann constant, you will get the temperature. This much of temperature is required for the fusion reaction. This much of temperature is required for the fusion reaction. 10 to the 3 into 10 to the power 9 Kelvin. But okay, after that, at such high temperature, the molecules of gas, means the molecule of hydrogen, this hydrogen molecules will breaks into atoms, and these atoms completely ionize. Obviously, all the electrons will remove. Ionize means all the electrons will remove. Not all the electron means it will these hydrogen, all the what is the meaning of all the electron? Because here is only one electron, so this one electron will be removed. So it will be like this. At such high temperature, the the molecules of the gas breaks into atoms, and these atoms completely ionized bare nuclei completely ionized to bare nuclei ionized to bare nuclei, okay, and electron cloud around them are obtained. Basically, you will get a plasma state. Now, what is the plasma state? From solid, if you will increase the temperature of the solid, it will become a liquid. If you will increase the temperature of liquid, it will become a gas. If you will again increase the temperature of a gas so much, it will become a plasma state. And what is the plasma state? There is a nucleus, and around that nucleus, there is an electron cloud. This is what? Electron cloud. So basically, you will get this nucleus and this nucleus. Now, both these nucleus will combine. And fusion reaction will take place. And we know that in fusion reaction, energy is released. So fusion reaction is exothermic process. And if it is an exothermic process, if once the fusion will started, it will be self-propagated, or you can say it will be self-sufficient. In terms of the binding energy, you can say in nuclear fission, binding energy always increases. Binding energy always increases up till iron. That means energy is released in nuclear fusion. Basically, what they want to say, energy releases in nuclear fusion. Nuclear fusion energy is releases. So what is happening here? If energy is releasing means some mass will disappear. So two lighter nuclei are combining to form a heavy nuclei, and during this process energy is releasing, and this energy is releasing because some mass is disappearing, delta M mass disappearing in fusion, so delta E energy will release. Now, earlier I told you for the fusion reaction there is a requirement of 3 into 10 to the power 9 Kelvin of temperature. So the temperature of 3 into 10 to the power 9 Kelvin cannot be achieved on Earth in a controlled manner. If you want to achieve that temperature, first you have to explode the atom bomb. That will give you a temperature of 10 to the power 9 Kelvin. After that, you will get that temperature. Then you will, then the fusion reaction will start with the help of this temperature. So to start the fusion of hydrogen atoms, we need to explode an atom bomb which produces initial kinetic energy required for fusion, and basically which will give the temperature of 10 to the power 9 Kelvin. And this is the principle of hydrogen bomb. So principle of hydrogen bomb is for the fusion of two hydrogen, there's a requirement of 10 to the power 9 Kelvin of temperature. How we will get that temperature? First we have to explode an atom bomb. By exploding the atom bomb, we will get a temperature and the sufficient kinetic energy. Temperature of 10 to the power 9 Kelvin we will get. Then the fusion of hydrogen will take place, and hydrogen fusion reaction will take place, and that is the principle of hydrogen bomb. After that, there are some nuclear fusion reactions written that is happening in sun or stars. Basically, here is 1H1 and 1H1, both are combining. It is having one proton, it is also having one proton. Both are combining so as to form 1S2. Along with this, one positron, antineutrino, and this much of energy is releasing. This is the first step. In second step, we have this. This is again combining with this. This is again combining this 1s2, hydrogen 1s2 is combining with 1h1, and we are getting helium 2he3. In this, there are 2 protons and 2 neutrons. Here is 1 proton, 1 neutron, and here is only 1 proton. So in this reaction, we will get helium, gamma particle, and 5.49 of mega electron volt of energy. In the third step, now we have helium. This helium will combine with the helium. So these helium will combine to give this. And along with this, we have this also 1h1, 1h1. I have written the number of protons and number of neutrons are there. And a release of energy of 12.86 mega electron volt. This much of energy will release. So in 3 steps, the fusion reaction will take place. So if you want to find the one step, means the whole equation in 1 step, if you want to write, so what you should do, you should multiply this step with 2, and you should multiply this step with 2, and you should add all these equations like this. Multiply this and add this, you will get this equation, and you have to remember this equation.
Sir, in step 2, how we got 2 neutrons?
In step 2, 2 neutrons. Neutrons are what? Mass number minus atomic number. 3 minus 2. Oh, sorry, it is 1 neutron. Very good.
Thank you.
It is 1 neutron. Okay. But here we are getting 2 neutron. 4 minus 2, 2 neutron we are getting. Okay. Here is 1 proton. Proton means atomic number is equal to proton. Neutron means mass number minus atomic number. So you will get this. Okay, one by one, take the screenshot. Hamza and Fawaz.
Yes, done, sir. Done, sir.
Done. Okay.
Done, sir. Done, sir.